The next topic in our class on aging is the topic of memory. So let's begin our exploration of memory and aging by looking at some of the conventional stereotypes we as a society hold with respect to older individuals and how we expect their memories to change. As a group, we believe that memory declines significantly as we grow older. That is not just little mild changes, but that there are pretty profound changes in the memories of all older adults. And not only that, we generalize this preconceptualizations to all forms of memory, memories for meaning, memories for essentially events and how to do things, procedures. We think all those memories decline. And finally, there's a shared belief in our culture that this memory decline in aging is not only large, but it's inescapable, it's universal. And there are many aspects of our society and our day-to-day lives that kind of serve to reinforce these stereotypes. Well, one important one is that there are many age-related pathologies like depression, cardiovascular disease, dementia, that are clearly associated with significant declines in memory. And so the people we know with these diseases happen to be old and they happen to have terrible memories. So we tend to generalize this to all older persons. In addition, if you look at our scientific literature, the classical literature over-relied on institutionalized populations. That is, people who were in hospitals or in other institutional settings like nursing homes. And why would those older people be in institutions? Because they were sick. Sick people tend to have problems with memory. If you're comparing young, healthy college students to institutionalized old people, surprise, surprise, you find big memory differences, big memory declines. So that has tended to bias the, if you will, the public's expectancy about what should happen to our aging as we aging memories. But there's other factors too in our individual lives that can reinforce these stereotypes. For example, when you retire compared to when you're still in working life before retirement, whether you be in school or whether you be on the job, at school and on the job, you have these highly structured environments based on where you have to be, when you have to be there, et cetera, that really serve as memory aids. And you're much less likely to forget appointments and to kind of always be where you're supposed to be because you have this regimen, this strict, if you will, situation that repeats itself over and over again and helps support your memory. Whereas in post-retirement years, your Tuesdays each week might be totally different in what you're doing. So you can't say, oh, Tuesday afternoon, 1 o'clock, I'm supposed to be at the history lecture. Your Tuesday afternoon at 1 o'clock could be different every single week. So without those external constraints, you're likely to make more memory errors. It's only natural. So less structured environments lead to more errors. I'm making more memory errors than I used to be now that I'm retired. That might lead us to essentially suspect that our memory and the memories of our other older folks we know are declining. And then there's self-fulfilling prophecy that's related to what I just said about less structured environments. I forget an important appointment, for example, age 65, and gee, I apply a lot of meaning to that missed appointment. Gee, am I getting more forgetful? Am I perhaps in the early stages of dementia? 25-year-old will never worry about that, so to speak. So a little memory slip, they might just write off in terms of, oh, gee, I need to be more organized. My schedule's too hectic, etc. I need to have a little bit better time management skills. Whereas the older person isn't attributing their problem to time management skills. They might be more likely to attribute it to some, if you will, change in their nervous system that might bode poorly for the future, and therefore that becomes a more salient event, and they begin judging their own memories in a less, if you will, um, positive light than a younger person might. So there are many, many, many different factors that conspire together to support this notion that memory pretty much sucks as we get older. But let's instead ask the question, what does science tell us about what happens to different aspects of memory as we grow older? And that's what the rest of this lecture is going to focus upon. So we're going to begin our exploration at about the same point in time where the whole discipline of gerontology began to emerge and grow in the United States and in Europe. And I like to refer to this period between 1965 and 1985 as the golden age of gerontology, because gerontology really came into its own then. And what is gerontology? It's the study of normative aging. And the study of normative aging began to emerge as a distinct scientific field during this time, this golden age of gerontology, distinctly different than the study of age-related diseases or geriatrics. And one of the things that motivated this, if you will, golden age of gerontology and the emergence of gerontology as a discipline, if you will, is that numerous scientists began to really document significant deviations from the conventional wisdom about aging on many things, in cognition and learning and memory, and saying, gee, if we're seeing all of these mismatches between what we think is happening in age and what really seems to be happening, it's time we really move beyond geriatrics and start looking at the healthy 80% of the population and seeing what's happening in their memory and their learning and their cognitive skills and their attentional mechanisms, etc. So as this movement evolved, gerontology departments proliferated across US universities, and even the National Institutes of Health established a separate National Institute on Aging in 1971. And its first director, Robert Butler, was very, very interested in behavioral aspects of normative aging, if you will, behavioral gerontology. And the National Institute on Aging has been very generous in fostering and funding behavioral research, particularly in the decades following its founding in 1971. So what I'd like to do at this point is I would like to begin by looking at a seminal study that really sort of captured this new focus on normative aging. That is this crossover from considering aging only from sort of a geriatrics perspective to a more modern perspective of looking at what we refer to as normative aging. And that first study is a classic study done by Helichka and Weiss, published in 1965, right at the leading edge of the golden age of gerontology. And what Helichka and Weiss noticed, what really kind of motivated their research, is they identified the fact that existing research with respect to aging memory was seriously flawed in many ways. One of the flaws I mentioned earlier, and that is that the studies focused upon using institutionalized older participants and comparing them to who? Healthy college students, so to speak. So that tended to really overestimate the magnitude of any declines we might see with age in cognition, memory, learning, etc. In addition, when one looked at memory studies in particular, what Helichka and Weiss found was that none of the studies of age differences in memory controlled for what could be referred to as the initial learning of the to-be-remembered stimuli. That is, if you present young and older people with lists to be remembered, if the old people didn't learn the list as well to begin with, surprise, surprise, when you tested their memory for the words a week later, they would remember fewer of the words. Was that because their memory failed? Or was it because perhaps they never learned as many in the first place? So with those issues at the forefront, let's look at the experiment that they performed that was quite influential in guiding subsequent studies of normative adult aging. So if you look at this matrix, you see a factorial study where two levels of age were explored, let's say 20-year-olds versus 70-year-olds in terms of age, and that we had two young groups labeled Roman numeral 1 and Roman numeral 3, and two old groups, Roman numeral 2, Roman numeral 4. And so altogether we have four groups, two different young groups, two different old groups. And how did these groups, these two different young groups and these two different old groups essentially differ from one another? Well, let's essentially begin this by looking at comparing the young group in Roman numeral 1 versus the old group in Roman numeral 2. These two groups represented the traditional approach to doing memory research. That is, they were given a list of stimuli to remember. They were given a list of stimuli to remember. And they went through this list 10 times, studying the list. Then a week later, they came back to the laboratory and they were asked, their memory was probed, they were asked to recall as many of the items as they could. And that's how their memory was tested. In that traditional approach, giving both groups an equal exposure to the stimuli, that is 10 repetitions through the list, we have no way of knowing whether the old people learned the material as well as the young people. And in fact, research would suggest that the old people probably didn't have enough time through just 10 repetitions to learn the list as well as the young people did. Now, what Holichka and Weiss did to get around that problem was they created these groups 3 and 4, a young group and an old group, and they had them study the list to what we call criterion. And what was the learning criterion that they studied the list to? They kept studying the list until they could go through it 2 successive times without making an error. That's a common way of operationalizing the fact that learning has occurred up to some standard level. So when you have the young and old people in groups 3 and 4 respectively study the list to criterion, that is until they make no mistakes on 2 trials in a row, what you can then assume is that they have both learned the materials equally. So they're equivalent in terms of learning, if you will, initial learning. So now when you bring the groups back a week later and test their memory, if you see a difference between groups 3 and 4, you can attribute that difference to memory mechanisms rather than to a mix of memory plus learning. Whereas if you compare groups 1 and 2, and in this study, where memory was not essentially controlled, learning was not initially controlled in phase 1 of the experiment, when you see a memory deficit, a memory performance deficit a week later, you don't know if it's due to a memory mechanism, a learning mechanism, or both. So let's take a look at what Holichka and Weiss found. Let's begin by looking at the traditional approach, and that is comparing groups 1 and groups 2, the young people who went through the list 10 times in phase 1, the old people who went through the list 10 times in phase 1, where initial learning was not controlled. It was allowed to go wherever nature would take it. And what they found there was the traditional result, a very, very large difference, as you can see by this green arrow here, showing you the gap between memory performance for the young group 1 and the old group 2 under the traditional conditions where learning was uncontrolled. And you see this large, very, very large effect. But now, interestingly, what happens if we look at the red function here, comparing the young group that essentially learned to criterion and the old group that learned to criterion, where initial learning was equalized, we see now that the decrement on the memory test 1 week later is now very, very small. So what we can conclude from this study, the conclusion that that Holichka and Weiss made, was that when you control For other sorts of decrements that can occur, in this case for learning, what you observe is that large age differences in long-term memory become actually much more modest. In this case, what we're seeing when we compare groups 1 and 2 is a small memory effect plus a large initial learning decrement, and that was masquerading as a large memory deficit. When we control for learning, we see that the memory decrement actually turns out to be quite small. And this led to sort of a sea change in the way we looked at memory and aging. Gee, maybe memory in older adults isn't so abysmal after all. And that unleashed a couple of decades of research that tried to find the boundary conditions on memory, cognition, learning research, and see what types of factors other than learning, memory, cognition could influence, if you will, performance on various tests. And this would enable us to titrate out what the true aging effects might be. And this guided research until the present day. So much of the research on, if you will, aging and memory that took place during the 20th century and actually into the 21st century as well has been guided by a somewhat classical model that's getting a little old and creaky in and of itself, but still very, very useful. A classical model of human memory called the information processing model. And so what we're going to do is we're going to first kind of review the structure of the information processing model. So we have a kind of a reasonable understanding of what it says and what its different components are. And then we will evaluate each of those components with respect to what happens in old age. So again, the information processing model, it conceptualizes human memory as being sort of analogous to the way a digital computer works. Digital computer has different stages in which it represents information, different processes in which information moves from one stage to the other. And in the information processing model of human memory, there are 3 distinctive stages of memory representation, namely sensory memory, short-term or working memory, and long-term memory. And then 3 important processes that sort of connect these stages together: attentional selection, which we've already looked at in some previous lectures. We'll look at it briefly again here. And then processes of storage, that is moving information into long-term memory, and retrieval, getting information from long-term memory back into working memory or short-term memory. So we're going to explore the interconnections of these stages and processes in the slides that follow. And then after we do that, we will look at each of these stages and processes and ask the question, how do these particular components of the information processing model change as we grow older? So we begin at the first stage of the representation of information from our environment in the information processing model. And that first stage is what we call sensory memory. Sensory memory, we actually have many different sensory memories. We have a sensory memory for sight or vision. We have one for sound, and sensory memories for the other senses as well. In a neurophysiological sense, the sensory memories could, if you will, be, if you will, represented in the primary sensory cortex for vision, the primary sensory cortex for hearing, and so on. And these cortices serve as temporary buffers for this information that's coming in from our senses. And as we saw in our lectures on attention, that the amount of information coming in from our senses and being represented in those primary sensory cortices is overwhelming, much more than we could ever process per unit time. So what has to happen is selective attention has to essentially extract task critical or mission critical information from that large array of information being imposed on the cortices. And what happens is, since attention is effortful and requires time to occur, the information has to be temporarily buffered to give attention the time it needs to extract the important information from the buffer. And so sensory memory is that construct, that phase of the information processing model, that stage of the information processing model that temporarily holds that information to give selective attention mechanisms enough time to pull out task critical aspects of the information array. And let's look at some of the properties of the sensory memory before we move on. The format of the information in sensory memory is a sort of a raw sensory neural activation in different low-level cortical areas. The duration of that information is about 500 milliseconds, typically we estimate it at. It only lasts enough time for attention to be able to operate at a particular criterion level. And then if we look at its capacity, how much information that the sensory buffers can hold, sensory memory buffers can hold, it's actually quite immense. It's very, very large, but it doesn't last very long. So it all depends on selective attention as to what information in that temporary buffer is going to pass on to subsequent stages in the information processing model. And here we see the second stage is working memory or short-term memory, and the contents of sensory memory are selected by selective attention, and that information is now recoded into a different format and passed to higher levels in the brain, from the primary sensory cortices up to higher levels in the brain. And that information is represented in a more sophisticated manner now. It is represented as what we would call perceptual or semantic codes, codes such as words or events or even melodies or sounds or tones, so to speak. And one of the things that's important for us to consider is that the duration of working memory now is, instead of just being 500 milliseconds, enough time for selective attention mechanisms to operate, it now has a duration of about 30 seconds max before the information decays and is lost forever. And perhaps the most important aspect of working memory is the number of these codes or items that can be held in working memory at any given time. You recall when we talked about sensory memory, we said it's full of this raw information that massive amounts of information can be stored temporarily in sensory memory. In working memory, we can only store about 7 of these codes or psychological objects in working memory at any given time. 7. That's not very many. And we'll see this is very, very prime real estate. And in theories of cognition, this limit on working memory is pretty much the gatekeeper of all human cognition. It determines how much cognitive work we can do per unit time. It's a very, very limited resource that has to be managed efficiently. So information in sensory memory that is not selected and transferred to working memory as a higher level psychological code is lost forever. It dissipates and it essentially vanishes into the ether, if you will. Once the items are deposited in working memory, they only last for about, 30 seconds at the most. Now, sometimes in working memory, we need to keep the contents alive for more than a few seconds before they fade away. And one of the ways we can do that is by accessing those items or by rehearsing them actively. And every time we access or rehearse an item, it gets a new lease on life. It's as though it's just been redeposited into working memory and the decay process starts all over again. So an example of rehearsal would be, suppose you had a telephone number that you had to remember. You looked it up and you were walking into the next room to pick up your cell phone to make a dial. One of the ways you could assure that you're going to keep that telephone number in working memory is to repeat it silently to yourself over and over again until you make the call. every time you repeat it to yourself, it's getting refreshed back to its full strength representation in working memory, and then starts to decay again. And if you repeat it several times, you never allow it to decay to a useless level and then fade completely from working memory. Now, the final components of the information processing model of human memory involve a long-term memory component. And long-term memory is extremely important. It's the seat of knowledge, the storage point of all of our experiences, all the events that we've experienced in our lives, all the things we've learned that are important. And not only that, in long-term memory, there are network connections between all of that information that we've stored that gives rise to meaningfulness. No particular piece of information is meaningful in and of itself. It's only the way in which that piece of information is connected in systematic fashions to other pieces of information that give rise to meaningfulness. And that's kind of what long-term memory is all about. So long-term memory, how do things get into long-term memory? Well, they start out in working memory as codes deposited in working memory, and then they are transferred, they're stored into the long-term memory system. That process is called storage. And if we could just store information in long-term memory but never be able to get access to it, it would be just a black hole that wouldn't be very useful. So we need to have a sort of complementary process we call retrieval that enables us, based on what's happening in working memory, to queue and then retrieve certain memories or knowledge, if you will, from long-term memory and bring it back into working memory, where it can be used and combined with current experience or other knowledge to form sophisticated, if you will, states of consciousness. The format of information in long-term memory can be in several different types of codes. It can be semantic codes, which are essentially networks of meaning. They could be episodic, that is, it relates to events, or it could be procedural, that is, codes that describe how to do things, so to speak. And we typically kind of think that we have like three actually separate long-term memory stores: a semantic store, an episodic store, and a procedural store. But we are not going to be talking about that distinction in this class. In terms of the duration of long-term memories, we started out seeing that sensory memory is very short, less than a second. Short-term memories, less than 30 seconds. The duration of long-term memories is pretty much unknown. We can assume that if the memories that are deposited in the long-term memory are done in such a way that they're very sophisticated and have lots of connections to other information in the network, the long-term memory network, that information could last for a lifetime. And also in terms of capacity, again, because of the way information is encoded in this distributed type of fashion in the brain, for all intents and purposes, the capacity is limited. I'm sorry, limitless. And nobody knows what the upper limit on the capacity of human memory might be. Perhaps if we lived for hundreds and hundreds of years, we would find out. But that's something that's going to occur in the distant future. It's not probably on our radar screen right now.